tonight, we have some unfortunate breaking news.
The 2022 year-end report for the Virginia Department of Transportation was just released, and the numbers are not good. In 2022, 59,404 people were injured in car crashes in Virginia. Over 1,000 died. These numbers have been steadily increasing over the past 10 years. This is a map of every fatal crash in 2022. Clearly, this is a major issue that needs to be solved. If we could identify key causes for these crashes, we can help keep our roads safe, improving the livelihood of all Virginians.
In order to do this, we found a data set that contains crash data for every Virginia car crash between January 2015 and July 2023. It contains data on each crash, such as location, injuries, and deaths, as well as other potential factors such as road conditions, time of day, and precipitation, which may contribute to the cause of crashes. We can use this data to build a machine learning model to predict when crashes will be and identify which key factors are similar among severe crashes.
Our data uses the KABCO scale for crash severity. This is a nationally adopted standard. In Virginia, first responders classify each crash on this scale. K means there was a death. A means a serious injury, such as broken bones, burns, or severe lacerations. B means a minor injury, such as bruises, abrasions, or swelling. C means no visible injury but complaints of pain. And O means there is no injury. We will use this scale throughout our project.
The first key takeaway from this data set is how unbalanced these classes are. There are over 700,000 crashes with no injuries throughout this 8-year period, yet only about 7,000 crashes resulting with a death. This makes sense because there are certainly more fender benders than deadly crashes. However, this can have a negative impact on our machine learning results because the most important results, the deadly crashes, is also the smallest one. This could lead to poor performance on that class for our model. For example, a model of simply predicting every crash will have 0 deaths would have accuracy of about 92%. For this reason, we utilize a synthetic minority overlapping technique, SMOTE for short. This process was developed by Nitesh Chawla in a 2002 research paper. SMOTE utilizes k-nearest neighbors to generate new samples of this minority class.
By using SMOTE, we will have a higher representation of the severe side of the KABCO scale, allowing our model to make better predictions. After generating additional training samples using SMOTE, we used 3 different machine learning models. The first was a linear classifier, the second, a logistic classifier, and the third, a support vector machine classifier. All 3 classifiers use a 1 versus rest technique for the classification task.
Ultimately, the logistic regression classifier using a 1 versus rest strategy performed the best. However, none of the models produced high accuracy, precision, and recall scores for each class. The logistic regression classifier had an average F1 score of 0.22. This is very bad. This means that the SMOTE technique, despite attempting to solve the problem of the non-injured class being overrepresented, did not succeed in doing so. Therefore, the many classes were being overclassified as injured or no injury happening, despite that not being true.
By using our model that can predict the severity of crashes, VDOT and first responders will be able to better allocate their resources and effort to preventing and responding to crashes.
For example, the Virginia Department of Transportation can find locations that correspond with a higher probability of severe crashes and work to prevent major accidents in this area by improving lighting, traffic management, or reducing speed limits. This would help stop severe crashes before they occur.
Additionally, first responders could use this model to manage staffing and placement of emergency teams. If they know that rush hour is a leading time of crashes in their area, they can increase staffing at those times. Additionally, during times of precipitation, they could use demand staffing and placement of vehicles to better prepare for the unfortunate increase in accidents during these poor conditions.
Overall, this model will hopefully help many different groups of decision makers work to improve the safety and decrease the number of both severe and minor crashes for all of Virginia.
And now, we'll kick it over to Bill for sports.